Okay, so beginning with the 3-class period long introduction to eigenvalue problems. That's before we even get into any methods for computing them. Okay, so I'm gonna come up with eigenwords. The strangest eigenword I ever saw was when I was in California at a sandwich shop, and little thing you shove your credit card into was labeled eigen payments. So I guess they thought it sounded cool. So, and I guess eigenvalue is one of a few mathematical terms mentioned in the Marvel Cinematic Universe by one of Peter Parker's professors. Okay, so so matrix name for which is easy to obtain the eigenvalues. That established last time. Matrices that are triangular reveals the eigenvalues immediately. Or if they're block triangular, you can then focus on each of the individual diagonal blocks. So now the next thing to consider is how to use similarity transformations, which were also introduced last time. Where A is placed by P inverse AP for some P, because it was also established last time that this kind of a transformation preserves the eigenvalues. Reduce A to a triangular or block triangular form. Okay. All right. Okay. So to get some idea on okay, on how to pursue this, we're actually going to assume that we have an eigenvector, an eigenvalue, just one, because our goal is to find all of them. So let's assume that X is an eigenvector. All right, so AX is equal to lambda X. And we're also going to assume that, and X has to be non-zero, but we're going to assume that it is a unit vector in the two norm sense. Okay. Right. And then we'll let P be a Householder matrix. Householder flexion satisfying this relation P times X is equal to E1. So this is why I needed the assumption that X is a unit vector, because P, well, normally I'd say P is an orthogonal matrix, but everything here is it could possibly be complex. Lambda might be complex, X might be a complex vector. So P could also be complex. So I need to use a complex analog for an orthogonal matrix. So PHP is equal to identity. So we don't say it's orthogonal, we say it's unitary. So that's like the complex analog of a real orthogonal matrix. And we used to normally say P is symmetric, but again, it could be complex. So we could say it's Hermitian. Okay. So, because of that, P is its own inverse. So we also have a relationship that, okay, well, yes. So these two together tell us that P inverse equals P. So that means that P E1 is equal to X. So now I'm going to look at the matrix obtained by transforming A in this manner, PHAP. Now, since PH is P inverse, that is a similarity transformation. So it will preserve the eigenvalues of A. But we're going to look at just the first column of this transform matrix. All right. So, well, PE1 is X. But AX is equal to lambda X. But PH is equal to P. And PX is equal to E1. So, first column of this transform matrix is all zero except for lambda in the first position. So the overall structure of a matrix is we have lambda up here, zero vector filling the rest of the first column, and then we have some unknown row vector that completes the rest of the first row, and then we have some matrix B down here. So this matrix is block upper triangular. So what that means is the spectrum of A consists of lambda, which is already known, and the spectrum of B. So, so in other words, we've cut the eigenvalue problem down to size a little bit. We've gotten lambda and X out of the way. And now we know what matrix to focus on to get the rest of the eigenvalues. Okay. So this whole process of using this Hausdorff transformation to separate lambda from the rest of the matrix is called deflation. So we can continue this process, like find if we have a way, right now we don't, but if we had a way of finding an eigenvalue of B, then we can carry out deflation on B. And work on a n minus 2 by n minus 2 matrix, and just keep going. So I think there's probably no greater cop out or no words more loaded than a mathematician can say than to say, continuing this process and in accumulating all of the householder transformations needed to carry out the deflation, until there's nothing left, we get some unitary matrix Q, HAU is equal to T. T is upper triangle. So, the way it's more commonly written is as a decomposition of A. So just rearranging the equation, I get this. And this is called the Schur decomposition. Okay. And the spectrum of A comes from the diagonal of T. So there is a way for any n by n matrix to use these similar transformations involving unitary matrices to reduce A to upper triangular form. And because it's done as a similar transformation, the eigenvalues of A are just diagonal entries of T. And unlike some other decompositions, for example, not every square matrix is a LU decomposition. Only symmetric positive deficit matrices have a Cholesky decomposition, but certain decompositions we have seen, like every matrix has an SVD of any size. Any square matrix has a Schur decomposition. If you allow column pivoting, every matrix has a QR factorization. Okay. Okay, so as I make it clear, we're trying to go in Q is a unitary matrix. But comes from accumulating all the householder reflections used to carry out each deflation. Okay. Okay. And how to do a Schur decomposition in MATLAB. If you do QT is equal to Schur of A. All right. You only have one output. I believe it's going to output T. Okay. Alrighty. One caveat I have to give about behavior of the MATLAB function. Okay. If A is real, then the MATLAB function Schur turns real matrices Q and T. Okay. So Q is a real orthogonal matrix. So Q transpose Q is equal to identity. And P is not upper triangular, it is block upper triangular. And the diagonal blocks are 1 by 1 corresponding to real eigenvalues of A, or they're 2 by 2 corresponding to complex eigenvalues of A that must occur in complex conjugate pairs. So then you have P is equal to Q transpose AQ, and this is called the real Schur form. Okay. When we get to a point where you see how to actually compute all the eigenvalues of a n by n real matrix, this is actually what we're going to go for, because even though we know that A may have complex eigenvalues, we want to avoid complex arithmetic for as long as we can. And it turns out it is possible using exclusively real arithmetic to do this. And so it's almost upper triangularized. Then when we see that we have 2 by 2 blocks, then we have a trivial amount of complex arithmetic to get a hold of those eigenvalues. But everything can be real up to that point. And it turned out to be no small issue of how to avoid complex arithmetic. It's one of the strokes of genius of the QR algorithm that it was possible. And it's very important to avoid complex arithmetic because like for addition or subtraction, that doubles the amount of floating point operations. For multiplication and division, it's even worse. Like with a straightforward approach to multiplying two complex numbers involves 4 multiplications of real numbers. I seem to recall, and don't quote me on this, I seem to recall there's some way to reduce it to 3, but still, it's bad. So, and every flop counts. So we're trying to avoid that complex arithmetic. Okay. Oh, I see what deal is here. Good. All right. Okay. Questions up to this point? Okay. Now, if you really, really want this form, even though A is real, okay, can do the following. Qt is equal to Schur A, and then you specify a second argument. Word complex in quotes. To get to decomposition A is equal to QTQH. T is totally upper triangular if A is real. So in that case, it'll compute a real Schur form first, and then just do a little bit of complex arithmetic to take those 2 by 2 blocks and break them apart into 1 by 1 complex conjugate blocks. Okay. Now, okay, I want to say something about the columns of Q from the Schur decomposition. So I've got like Q, Q1, Q2, up to Qs. These are orthonormal vectors. Okay. Now, Q1 is an eigenvector, but just Q1. The other ones are not. There's not really a simple relationship. So these vectors overall are called the Schur vectors. Well, unfortunately, aside from Q1, there's no simple relationship between eigenvectors of A and the Schur vectors of A. So what we can say is, if I multiply A by one of these Schur vectors, well, that's the same as A Q, a matrix Q times EJ to extract the jth column of Q. But AQ is equal to QT by rearranging the equation from the Schur decomposition. And because T is upper triangular, that's going to be a linear combination of the first K, the first J Schur vectors. So since AQJ is linear combination of the first J Schur vectors, we could say that the subspace spanned by the first J Schur vectors is an invariant subspace. Okay. So at least we know that much. When you have invariant subspaces, you can use that to find eigenvalues and eigenvectors more efficiently. Okay. All right. Now, there is a situation though where there is a nice relationship between the Schur vectors and eigenvectors. Okay. Let's suppose that A is referred to as a normal matrix. And what I mean by normal matrix is that it commutes with its own adjoint. AJ is equal to AH. Okay. Now, here's some examples of a normal matrix. If A is if A is a real matrix and it is symmetric, so A is equal to its own transpose, and since it's real, it's also equal to AH. So it certainly will commute with itself. Or if it's real and skew symmetric, so A is equal to minus A transpose. So those are examples of normal matrices. Now, it can be shown, and I'm having difficulty remembering exactly how to show it, unfortunately. Don't have it written in my notes. But if A is normal, then T, which is equal to QHAQ, is also normal. Actually, I think that in particular would not be hard to show. PHT, which is equal to QHAHQ, QHAQ, but then you simplify that, that's the same as QHAHAQ, but A is normal, so AHA is equal to AAH. And then I stick a QHQ in the middle. That's identity. Wait. Something's wrong. Oh, that should be H here. Yeah, okay. But that is TTH. Okay, that I can show. That's if A is normal, then so is T. What is more difficult to show is that because T is normal and upper triangular, but the only way that can happen is that T is diagonal. So what happens in that case is the columns of Q, Q1, Q2, or Qn are eigenvectors. Of A. So Schur vectors are equal to eigenvectors in the case of a normal matrix. Yes, it's going to drive me nuts trying to remember how that's shown. That must be diagonal. It's something I remember hashing out a long time ago. Probably I made a homework problem that I didn't assign. You know what? I'm going to look. CW chapter 6. Oh, yes, exploration 619. Let T be a normal upper triangular matrix, prove that T is diagonal. And I did not give a hint. Yeah, but I have to remember what it would be.
Work it out on the board. We want luck.
Yes, but it's on video. Literally everyone can look. Okay. One of those things that has to be done like column by column or something like that. So, okay. I'm going to try see if I can show this for a particular entry. Certain like so one way to try to show this is if you're looking at the IJ entry of a product. And if it's offset, so it's off diagonal entry, that presumably must be 0. Following from the upper triangularity of T. I'll try that and see how it goes. If it runs to a dead end, then I'll stop. Okay. So TH P. We have a 2-1 entry. That's going to be a product. Right, so Hermitian transpose entry 2K, and then the K1 entry of T. When it comes to Hermitian transpose, then we have K2 conjugates K1. Now, P is upper triangular. So if the row index is greater than the column index, the entry must be 0. So this is 0 for all K greater than 1 due to the upper triangularity. So this is going to be P1, 2. So this sum only includes K equal 1. Conjugate P1, 1. So that's what we have here. Okay. So then I carry out the same process of ETH. It's 2-1 entry. All right, so then I look at E, row 2, column K, E, K1, but that's 1K. Conjugates. All right. Now, okay. Now, when K is equal to 1, I get T2 1. That's going to be 0. So K equals 1 doesn't produce anything. When K is equal to 2, I'll have T2 2, T conjugates K1 2, and then this will continue. No, 2 3. T conjugates 1 3, and so on, all the way up to T2n, T conjugates T1n. But these have to be equal because of T being a normal matrix. I feel like something is wrong, but I don't know. Okay. Now, I'm wondering if I should chose a different entry than 2-1, but it seems like a logical choice because it's like you think of it as like the first off diagonal entry as you're going from up to down. Well, thanks. All right. Okay. All right. I'll revisit that. Okay. I want to consider like some a whole other approach I was supposed to take. Okay. Okay. Now, back to where we were. Q, H, A, Q, is equal to a diagonal matrix D. That's what we found if A is normal. Okay. So that means that A is diagonalizable. Diagonalizable is, the definition of that is it's a similar to a diagonal matrix. In other words, there's some similar transformation that'll make a diagonal. And I mentioned it's also unitarily diagonalizable just because the matrix that brings that about is unitary. Although that's not the main point I want to make right now. Okay. So if A is not normal, it can still be diagonalized. We might have a situation like this: P inverse AP equals D, where D is diagonal. In which case, if A is not normal, P would not be unitary. So we still say it's diagonalizable, it's just not unitarily diagonalizable. That's it. I say it might be. We don't have a guarantee. Okay. So okay. The simplest answer I can give to this question is if it has n linearly independent eigenvectors. Okay. Since each eigenvalue will have at least one linearly independent eigenvector associated with it. But if lambda is a repeated eigenvalue, if it repeats a certain number of times, it's not necessarily going to have that many linearly independent eigenvectors. Okay, so what I could say about P is the columns of P are the eigenvectors of A. So anytime you have a similar transformation like this that reduces A to diagonal form, that tells you what the eigenvectors are as well as the eigenvalues. I'll also say that the rows of P inverse are the eigenvectors of a transpose. So we have that relationship too. If I took transpose of both sides of this equation, I'd have P transpose, A transpose, P inverse transpose equals D transpose, but D is a diagonal matrix. So if P diagonalizes A, then P inverse transpose diagonalizes A transpose. All right. Okay. So I should mention that regard to MATLAB's I function. If you have XD equals I of A, that then you do have this relationship, A times X is equal to X times D. Now this would imply that X inverse AX is equal to D, but that is only true if X is invertible. So only then do you know that A is diagonalizable. So if A is not diagonalizable, and A is n by n, you're still going to get an n by n matrix here. It's just that this matrix X will not be singular. There'll be like some columns will be linearly dependent, so you won't be able to go from here to here. Okay. Now, one case where we know we have A diagonalizable is the following. If we have two distinct eigenvalues, lambda 1 not equal to lambda 2, and x1 and x2 are corresponding eigenvectors for lambda 1 and lambda 2. This would be lambda 1, 2. Then we can say that x1 and x2 are linearly independent. So in general, distinct eigenvalues always lead to linearly dependent eigenvectors. So we can extrapolate from this, again, the whole continuing this process thing, and say that if A has n distinct eigenvalues, then we can say for sure that A is diagonalizable. So that's the nice case. Because, like I said, each eigenvalue will have at least one linearly independent eigenvector associated with it. The problems begin if eigenvalues repeat. Then you don't know how many linearly independent eigenvalues are repeated linearly independent eigenvectors a repeated eigenvalue has. So, this is where you talk about the multiplicity of an eigenvalue. Kind of like, understand the concept of multiplicity of a root of a polynomial. And we saw last time, eigenvalues are polynomial roots. But because we're talking about eigenvalues and eigenvectors, we actually have more than one notion of multiplicity. the algebraic multiplicity of an eigenvalue lambda is equal to a multiplicity of lambda as a root of a characteristic polynomial A. So if you have some eigenvalue A and you have a factor of lambda minus A to the 5th power in the characteristic polynomial, then we say that the algebraic multiplicity of the eigenvalue A is 5. So this is a, yes.
Is the last part in the first line lambda belongs to lambda of A?
Yes.
Okay.
That's just concisely saying
I-
that lambda is an eigenvalue.
Okay, it's not super visible.
Oh. What do you mean by super visible?
It's faint. It was a bit faint, yeah. Okay, that's a lot better. Thank you.
Okay. All right. Now, the less familiar notion of multiplicity is geometric multiplicity. So it's algebraic, and now geometric multiplicity of lambda, also an eigenvalue of A, is the number of linearly independent eigenvectors. That are corresponding to lambda. Okay. Another way of putting it is equal to the dimension of the eigenspace corresponding to lambda, which is just a span of whatever eigenvectors lambda has. So if it's possible to find, say, 4 linearly dependent eigenvectors for a given eigenvalue lambda, then the geometric multiplicity would be 4. Now, so the question is, how do the algebraic and geometric multiplicity relate to one another? What we have is the geometric multiplicity. That must be at least 1, and is always less than or equal to the algebraic. So the algebraic multiplicity is an upper bound on how many linearly independent eigenvectors you could hope to find. So a troublesome case is when the geometric is strictly less. So the geometric multiplicity is strictly less than algebraic. In other words, you do not have enough linearly independent eigenvectors that match the multiplicity of lambda as a root of a characteristic polynomial. We say that lambda is defective. So whenever there's that mismatch between the two multiplicities, that's when things go south. Yeah. Okay. Pause for any questions or writing. Actually, one other term I'll throw out there that's also related to multiplicity. If both multiplicities are equal to 1, I would say that lambda is a simple eigenvalue. So we like simple eigenvalues. Those are easier to work with. Right. Now, if A has any defective eigenvalue, so there's a slight mismatch between algebraic and geometric multiplicity, then we can say that A is not diagonalizable. So, because then it's not possible for A to have a full set of n linearly independent eigenvectors. So, in other words, there's no similar transformation you could possibly make that would reduce A to diagonal form. Now, you can still reduce it to upper triangular form and get the eigenvalues that way for Schur decomposition, and that's why numerical methods for computing eigenvalues focus on a Schur decomposition because it's always known to exist. That can be a lot more challenging to get all of the eigenvectors of A than to get the eigenvalues. Except for the case where A is symmetric, then everything works out so much more nicely. And that's what I'm actually going to talk about the symmetric case as a separate problem, because there are a lot of simplifications that happen compared to the unsymmetric case. It's a lot easier to get the eigenvectors in. So if you can't reduce A to diagonal form, is there some other relatively simple form that we can reduce A to? And the answer is yes. So every matrix has, in addition to a Schur decomposition, a form called the Jordan canonical form. And I remember in a graduate level pure linear algebra class learning about this, well, attempting to learn about this, not really understanding any of it. There's actually numerical linear algebra that helped me grasp it years later. So the idea is X, it's some matrix, vertical matrix X, that X inverse AX is equal to some matrix J, and that's J is referred to as the Jordan form, is not necessarily diagonal, but what we can say it is block diagonal. And each Ji is called a Jordan block. And it has this form. It has an eigenvalue of A along the diagonal. And then it has ones along the super diagonal, and everything else is zero. So it is, another way of putting it, it's upper bidiagonal. So that's the best we can do. That we can, so we can reduce any A to a matrix that is almost diagonal. Okay. Now, there's a relationship between these Jordan blocks and the multiplicities of eigenvalues. So P, the number of Jordan blocks that we have, that is equal to the number of linearly independent eigenvectors of A. So if A is diagonalizable, P would be equal to N. And each Jordan block would therefore have to be 1 by 1 because J is N by N. So the sum of the sizes of the blocks has to equal N. Okay. The number of Jordan blocks that feature lambda I as an eigenvalue, that is equal to the geometric multiplicity of lambda I. So it is possible for a single eigenvalue lambda I to have more than one Jordan block associated with it. So each one of these blocks corresponds to one linearly independent eigenvector. So then the sum of the sizes of the blocks that have lambda I on a diagonal, that is equal to the algebraic multiplicity so the only way A is going to be diagonalizable is if you have all 1 by 1 Jordan blocks, each Jordan block corresponding to a linearly independent eigenvector. So then geometric and algebraic multiplicities will be equal. Right. Oh, okay. Now I'll do an example involving Jordan form, get into what it can tell us about eigenvalues and eigenvectors. So here we have Jordan form for a 6 by 6 matrix. So the first Jordan block corresponds to the eigenvalue 2. So the block is 3 by 3. Then we have a second block, it's 2 by 2, corresponding to the eigenvalue 3. Then we have a 1 by 1 block that also corresponds to the eigenvalue 2 again. So I'm going to make a chart. And listing each distinct eigenvalue we have. And then we can look at the algebraic and geometric multiplicities of each one. So the eigenvalue 2 has 2 Jordan blocks associated with it. So its geometric multiplicity is 2. But now if we add up the sizes of those 2 blocks, 1 by 1, 3 by 3, so the algebraic multiplicity of lambda equal 2 is 4. So it's a quite effective eigenvalue. But But the other eigenvalue 3 is also defective because there's only one block associated with 3, so it only has one linearly independent eigenvector. But that block is one block is 2 by 2, so it has an algebraic multiplicity of 2. So in other words, the characteristic polynomial equal to lambda minus 2 to the 4th power, lambda minus 3 squares. But we only have 3 linearly independent eigenvectors for the whole matrix. So in a sense, it's not even close to being diagonalizable. Any questions about that example? Okay. Now, Jordan form, something we'd love to have, because you can tell us all about the eigenvectors in the matrix. Problem is, it is not practical to compute. I should emphasize in floating point arithmetic. If somehow you can perform exact arithmetic, or you have variable precision arithmetic, go for it. But otherwise, it's not a good idea. And the reason why is that the Jordan form J is not a continuous function. Of the entries of A. Most things we compute in numerical linear algebra, including eigenvalues, do depend in a continuous way on the entries of A. But Jordan form does not, because, so to give you an idea, suppose we have, go ahead and compute the eigenvalues of A by whatever method. We have two eigenvalues that are extremely close to each other, like their difference is maybe on the order of round off error. And let's simplify matters and assume we're just dealing with a 2 by 2 matrix, so we compute the only two eigenvalues. So if the two eigenvalues really are supposed to be distinct, then this would be our Jordan form. They would be diagonal. Or what if they are really meant to be the same eigenvalue? If lambda 1, and what if that eigenvalue happens to be defective? Because if they're distinct, we're computing what are supposed to be linearly independent eigenvectors, but what if those eigenvectors are nearly linearly dependent? Maybe they really are supposed to coalesce into one eigenvector. So then you have a Jordan form like this. We don't know which is the right one. So a little bit of rounding error can flip this 0 to a 1. That's a big difference. So that's what I mean by not being a continuous function of the entries of A. So a tiny change in A could flip Jordan form entry from a 0 to a 1. And so that makes a total non-starter for practical computation. And if the matrix is well behaved, if it's diagonalizable, we're really computing Schur decomposition, Jordan form, all the same. But and I believe there is mathematical software, but we'll try to compute the Jordan form for you. but I only hope the documentation for that software indicates the risks of getting an unreliable result. Okay, so that's why in the rest of my coverage of eigenvalue methods, we're not going to deal with short form, at least not for practical computation. It is useful in numerical linear algebra from an analysis standpoint, because if you're trying to compute the Schur decomposition of a matrix instead, something you know you can get, something that does depend continuously on A. If you have eigenvalues that are clustered close together, you can still have problems computing those eigenvalues and the eigenvectors that go with them. And the Jordan form can be helpful in analyzing that difficulty. But as far as actually trying to compute it, no. Okay. So, just saw your comment, Nima. Cool. All right. Oh, just about out of time. Or questions about anything? Maybe one more day of going through all this analysis. And then we'll start computing stuff. Okay. So until then. Wait a minute. Okay. For a second I thought I wasn't recording, but I was. Okay.